So this is where we left off, and we said that if a molecule rotates light left-handed, we give it a negative, and if the light rotates light right-handed, we give it a positive. Now, I've got on this slide often called dextro and often called levo, but I don't want you to get confused, so I'm going to leave that off, and we're just going to pretend like that doesn't have a name at all, because I don't want you to get that confused with the dextro and levo for the molecule. So there's dextro-levo for the molecule, and then there's dextro-levo for the light and which way it turns, so I don't want you to get confused. So we're going to pretend like there is no name associated with the positive and the negative. All right, that keeps things simple for us at this time. We also said that it has nothing to do with stereochemistry, right? If a molecule is left-handed or if the molecule is right-handed, well, that has nothing to do with the way it will rotate light. Right? So we said that we can have an R plus, but we can also have an R minus. We can have an S plus, and we can have an S minus as well. So this has to be measured, or it has to be looked up into a textbook somewhere. So here's the nice young gentleman that decided to give you the polarimeter field and to talk about stereochemistry and the way that molecules bend light. And his name is Jean-Baptiste Biot in 1774 to 1862. He looks pretty sitting in there in that chair. So ladies and maybe gentlemen, if you would like to date this man, you know, there you go. What a sight to look at in the mornings when you wake up. So studied plane polarized light. That's basically what he did for his life, at least in the later years. And he looked at how molecules would rotate light. And he knew that some went left and some went right. The problem, though, is that he actually had a completely different theory of what light was. He did not say that light was a wave. We know now that light energy is wave, and we can basically take these waves and use them to our advantage. But during that time, he said that it was a small packet of energy in a way. So it comes to you basically in one form of another, and that's about it. They did not have waves. They did not have wavelengths. But we know that that's all true. They are waves. He also loved to study meteorites. He was one of the few that believed back in the day that rocks could fall from the solar system. And that if you could gather these rocks up and if you could take them back to a laboratory, you could understand more about the solar system and about what was in outer space and way up into the sky. Because during 1774 to 1862, man had not walked the moon yet. So all of that was unknown in a way, and they had no clue what was out in outer space. The percent composition would provide you details on the elemental composition of the solar system. So if they could bring those meteorites or those rocks that fell from outer space into a laboratory, and they could break them down, and they could study them, and they could analyze them, they could do something like a metal panel, and it would tell them what kind of metals would be present in the solar system itself, and if that was different than what was on Earth. He also stated that light could be rotated by molecules clockwise or counterclockwise, and he was also on the balloon with Gay-Lussac. So if you've ever heard the story of Gay-Lussac, Gay-Lussac was basically a scientist back in the day that really studied gases, and he loved the relationship that gases had with pressure and temperature. So he basically was on the very first hot air balloon, one of the first, where temperature could make basically a hot air balloon expand and make it lift up off of the ground, and they could ride it like Dorothy. However, the problem is that no one really knew what hot air balloons were back in the day, and when Gay-Lussac came crashing down near Paris, all of the citizens went crazy, and they thought it was some kind of alien creature from the sky, or some kind of angel if they were very religious, and they began to attack the balloon after Gay-Lussac crashed it down. But Jean-Baptiste Biot was on that balloon with him. It just wasn't Gay-Lussac. So here's a depiction of a molecule, a chiral molecule at least, and we told you the definition of a chiral molecule. It's a carbon with 4 different attachments, right? And that's what you're seeing here in the diagram. You see a dark purple and a pink and a green and a yellow. And the reason is because each color represents something completely different. So in order for a molecule to be chiral, there's also some other things that have to be kind of assumed when we say 4 different groups. So the first one is that no double bonds are allowed. If you have a double bond to a molecule, then you can't have 4 different groups, right? If you've got 2 bonds to the pink one, then that means this carbon's got to give up a 4th bond somewhere that it has right now. So let's say that you erase this purple one. So you free up a bond and you do a double bond to the pink. Well, that's just 3 groups now, and you can't really have anything that's chiral with 3 groups. You really have to have 4. So 4 is the requirement, which means by default, double bonds are not allowed, triple bonds are not allowed. They all have to be single. Next, hydrogen does count as a group. So very often you'll hear us say, oh, forget about hydrogen because it doesn't really matter in this case. But when it concerns stereochemistry and chirality, then hydrogen does matter, and hydrogen does count as a group if it's present. So if you look at these 4 molecules down here at the very bottom, these would be very good test questions or something that you might see, and it gives you a molecule and it gives you a little star onto a carbon. And the reason that the star is there is because they want to know, is this going to be chiral or not? Yes or no? So if you look at that particular carbon and you look to the left, you see a 3 carbon chain to the left, right? So 3 carbons in total. And then if you look to the right hand, you're going to see 1, 2, 3, 4 carbons in total. So those 2 groups are different. And then that carbon also has a hydrogen attached to it. So there's your 3rd different group. And then the carbon has an OH group in front that's attached to it. So there's your 4th different group. So that asterisk carbon is a chiral carbon. All right. Now, if you look at this 2nd carbon into the chain, is that one chiral? Yes or no? Well, we look to the left and we see 1 carbon with 3 hydrogens. So there's a methyl group. So there's 1 group. And then we look to the right hand and there's 1, 2, 3, 4, 5, 6 carbons in total, with an OH group hanging off of it. So there's your 2nd group. You take the whole thing or nothing at all. And then your 3rd group will be the hydrogen that's on that carbon, and your 4th group would be the 2nd hydrogen on that carbon. So because of that, those 2 hydrogens are the same, and you do not have 4 different groups, and therefore that carbon would not be chiral. The 1st carbon would not be chiral. The 3rd carbon would not be chiral. Notice there's 2 hydrogens on that 3rd carbon, 3 hydrogens on that 1st carbon. All 4 have to be different. If you go to the 5th carbon, that would not be chiral. The 6th one would not be chiral. The 7th one would not be chiral. And the 8th one would not be chiral. Because again, they all have more than 1 hydrogen that's attached. So that carbon with the asterisk is the only chiral carbon in the entire molecule. And that carbon, we could put an R or an S depending on how they're given, and we can determine if that's left-handed or right-handed. The problem though is that we cannot determine if that molecule will rotate light left-handed or right-handed. We're actually going to have to put that into a polarimeter and actually measure it in order to determine that. All right, a little more about the definition of a chiral compound. It's basically a mirror image that you cannot overlap. That's what chirality basically is. So when we say, is this molecule chiral, we often think, oh, well, this group has 4 different groups, right? And those 4 different groups make it chiral. Well, that's true. But the other kind of hidden part of the definition is that when you do a mirror image of a chiral molecule, they do not overlap. And that is why we have the R version and the S version. If they overlapped, then all of a sudden there's no difference between the 2, right? So here up at the top are chiral objects. You take your left hand, you take a mirror image of it, and you'll get your right hand. And if you do not twist and turn, but you just try to overlap those 2 images over top of each other, they're never going to work. Your ear is the same way, and this basically is the seat of your car. So if you took a mirror image of the inside of your car, the steering wheel would flip to the right hand side now, and then you would try to take these 2 images and try to overlap overlap them, and they're not going to overlap. However, down here at the bottom, these are achiral, which means they are not chiral molecules, which means that they do not have 4 different groups on them. So to give you an example or something to relate it to, here's a chair. You take the mirror image of it, it looks just like the original, and you can overlap those, and those are fine. And here's a fork, and you take a mirror image of it, and you can overlap those, and those perfectly line up, so therefore that's an achiral molecule. This does not have 4 different groups on it. And then here's a glass, and you take a mirror image of a glass, and you can take that image and overlap it, and they perfectly match up again. So that is an achiral molecule, which would be representative of a group that does not have 4 different things attached. Now, I told you that we would talk about the instrumentation, and here's the instrumentation for polarimeter. So what you're seeing on the screen is an area inside of the polarimeter, and that polarimeter has to have a light bulb in order to work. Some of the old school polarimeters, you're actually going to see the light bulb because you're going to have to turn it on and you're going to have to put up the sample chamber to it. However, with our automated polarimeter, you no longer have to do that. You basically turn the instrument on, the bulb shows up on the inside of the instrument, and it really hides it from your eyeballs. So you don't really ever see the light bulb inside of the polarimeter itself. But you do have to have a light source, and the light source will basically give you normal light, and that normal light consists of all wavelengths, right? So whenever you look at visible light, you're seeing every color of the rainbow, Roy G. Biv, and that's why when you put a prism or a water droplet through normal light on a hot sunny day while it's raining, you see rainbows in the sky because those water droplets are serving as prisms and they're dividing the light up into the colors. And the same thing is going to have to happen here. We have this light source, and this light source is shown in all directions. So if we use a normal light from a light source like a normal light bulb in your house, then we're going to have problems. There's going to be variables that we need to take care of. So in order to do that, what they decide to do with the polarimeter is they choose what we call a sodium D lamp. And that D basically represents the wavelength of 589. Okay, so that wavelength of 589 is good because that means that that light bulb is only going to give me one wavelength, and that is it. I'm not going to get a light source that gives me red, orange, yellow, green, blue, indigo, and violet like normal. So sodium D only gives me one wavelength. That one wavelength is 589, and that one wavelength is basically shot out from the light bulb, and that's it. The problem, though, is that it still goes in all directions, but we've eliminated all of the variables with all of the other wavelengths that might come along with a normal light. We don't want the colors of the rainbow here. We want this simplified, so 589 is what they decide to do. That's also why very often, if you look in the Merck or the CRC, you're going to see the angle or the polarimeter reads with a 589 or a D listed with that number. The D represents sodium D lamp, and the 589, of course, represents the wavelength. So depending on what you look at and what textbook or what reference book you use, that's what you're going to see associated with those numbers, and that is why they're present. Okay? They're letting you know, yes, this is sodium D, and you should be using sodium D in the instrument. So that light source will give you light in all directions, and we have to narrow down that field. We only have to take in one direction, and that is it. We have to filter out everything else. And that filter is basically what we call the polarizer. So there's a small slit, if you want to imagine that, in the polarizer, and the polarizer will only allow one direction of light to escape through. So this one direction of light may be up and down in this case, and only up and down will go through the polarimeter, and now we have cleaned up our light source, and we are ready to basically give that light source to a molecule. If you allow all of the directions of the light to escape through, you will never be able to determine which way the light will be rotated by the molecule, because if all directions are going through, then that means all directions will go through the molecule, and how on earth are you going to tell rotation? You can't. So that's why you're seeing here an up or down getting filtered through. Only one direction and that is it. So this is what we would do if we were going to blank our instrument. We would not put a molecule on the inside, and we would allow the machine to allow the light source to give it light, and we would filter it through one direction only, and this would allow the machine to tear itself out to a reading of 0. That is kind of our blank. There's nothing present in there. Now, when I say nothing present, you typically have to put your solvent in at least. So if you've dissolved your stuff in water, you put water in there and you allow it to blank itself. If you've dissolved your stuff in acetone, you put acetone in there and blank it. If you've put it in methanol, you put methanol in and blank it, right? So whatever your solvent is, that is what you're going to put into the polarimeter in the very beginning. Those solvents are chosen because they probably are not chiral, which means they're not going to rotate light in the first place, but we just want to be safe. We want to make sure that it is 0, and that if there is any slight contamination in the solvent that would have a chiral molecule, that would rotate the light left-handed or right-handed on us, that we eliminate that out. We do not want the solvent to play a picture in our reading. Okay, then the next thing is that we would take out that sample chamber and we would put our molecule on the inside. Okay, now if the molecule is achiral, then that means that this molecule should not rotate light at all, right? And if it doesn't rotate light, if we have put a polarizer in that only allows the up and down version of light to come through, then the up and down will stay as it travels through the sample, and that up and down will continue out the other end. So the polarimeter would actually see this and say, well, this light didn't move. And because that light didn't move, you've got a reading of 0 now. So they bring out a number close to 0, and that's why you see the number as you do on the display. However, if you put a chiral compound in, what you would see is that these arrows would begin to turn. So if you give it up and down light, this molecule is going to begin to turn it. It will either go left-handed or it will go right-handed. And you would start to see that light slowly shift, little bit by little bit right, or little bit by little bit left. And what would happen is that at the end of this polarimeter, then this molecule has rotated the light and it's not in the original direction. So the detector of the instrument on the other end is going to say, well, I don't see any light. What has happened to it? I thought it was supposed to be pointed up and down. So the instrument will begin to rotate the viewpoint at the end of the sample chamber, and it will rotate it until it matches the original light again, until it can actually see the light just like it did before you put the sample in. And depending on how it rotates, did it have to rotate it left or did it have to rotate it right? You'll see that number on the screen. And then how much did it have to rotate in order to get to that point? Well, you'll see that onto the screen as well. So that is how the instrument does its job. There is an automated rotator at the end of that sample chamber, and it will rotate left-handed or right-handed, and it will measure how far it had to rotate, and that's the number that pops up on your display screen when you begin to use this polarimeter. Here's the picture of the polarimeter. This is your digital display over here to the side, so it looks like this molecule rotated light positively, or there would be a negative there in front. And it did so with 10.45. So that is a rotation unit that is associated with the molecule and the light energy. Here on the center, you can see the sample chamber or the sample compartment. There's a lid that basically will flop down, and you put a stainless steel tube that has your molecule completely filled on the inside into the chamber, and you close this door up, and then you hit measure onto the computer screen. It will take a couple of seconds. It won't take long, and it will also give you statistics. So it will do multiple readings, and those multiple readings will be averaged out and displayed on the screen, and standard deviation will also be associated with it. The automated polarimeter takes the guesswork out. So if you've used or if you've been in another chemistry course, and this chemistry course basically has allowed you to use the old, cheaper polarimeters, these are very subjective because you have to be the eyeballs of the instrument, and you have to rotate, and you have to go until you see the light come through again. And if that's the case, then I can take two analysts in a laboratory and they give me two completely different answers, but they might be close, but they might be different enough to have the sample fail and then pass in one version or the other. So automation takes the guesswork out. You no longer have to do that anymore. The sample tubes that we have in our laboratory are 1/2 of a decimeter, and the reason that I say that is because that's very important when it concerns our calculations that we'll talk about a little bit later. Here's the old school polarimeters, something that you might have seen in a laboratory at some point in time. So here's the view piece. You are the detector for the instrument. It doesn't have anything automated. And then over here to the end, this is the light beam, and you can kind of see that turned on, the bulb on the inside, and that light energy is going into the sample compartment, which would be in this long cylindrical tube. Here are your cells that you would use for those polarimeters. You would fill up your sample to the very top, put the lid on it, make sure you overfill it. That way there's no air bubbles on the inside, and then these tubes go onto the inside of the polarimeter, and you would turn the light on and you would look through the view piece and you would rotate this left-handed or right-handed until you saw the light come through. Here are your field views, which means that if you look through the eyepiece, this is what you would be seeing inside of the polarimeter. So number 1 is above or below what they would call optical zero, and this is traditionally what people would see in the very beginning. A dark area that is separated by two lighter halves. Here, below or above the optical zero. That just means you maybe have went too far and you're on the other side now, right? Because this will actually rotate 360 degrees. So depending on where you are, that's what you would see. And then number 2, it says field at the optical zero. Notice that the dark area has went away, and instead you're seeing some light come through. I really would wish that number 2 would be all yellow, because that would signify to you that light is coming through now and it's matching basically the other part, and that's where you would stop the reading instead of using the gray that you see in the eyepiece. So there's the old school polarimeter. We do have some of these, but we do not use them because we do have an automated polarimeter that does the job instead. So that's the story with the instrument, and in the next video we won't really necessarily talk about calculations yet, but we'll talk about these sugars and what they begin to do.